Thank you very much for inviting me. Pardon me if I keep moving my glasses around. But first off, I'd just like to say thank you to the previous speakers. So Pit, Samudra, we have Sam Davis. There's a Sam up in the background there. Also Yi, Fabian and Maria, the PhD students. You all did a great job. Thank you very much. So Willem asked me to come over and give the closing, speech for the DARE, and asked me to, just speak for about 10 minutes. And so I said, 10, 15 minutes, what would you like me to speak on? He said, just about the future of data science. And I thought, okay, well, that's going to be a little bit hairier. It's a big topic, and to deal with in 10 minutes is rather, a stiff brief, if you like. But I thought, what would I think would be one of the future big challenges of data science that perhaps if I imagine myself as Tom Cruise that I could ride through this door and get to, but it's not going to be easy to do. So with that in mind, and I'm going to get to that, but the first point we want to think on the way through is actually what parts of the mission have we accomplished? And I think what we have done is quite a bit on the way through, okay? Certainly the delivery of fundamental, impactful and industry-ready research. So fundamental in the statistical sense, that's what I'm going to be talking about, and also impactful in the industry for industry and our domain partners. I'm going to actually go forward just one, and then I'll go back. Keep in mind, what I'm about to show you is surface currents on the northwest shelf of Australia, okay? Okay, so on the right-hand side there are the surface currents in the northings and eastings, okay? At the very far left, at the zero value on the x-axis is time zero, and their forecast horizons going into the future. The black line are the observations, but we're pretending we don't know them. The red lines are our forecast. It's a statistical model, a Bayesian hierarchical model that's doing an average forecast. We're getting the posterior predictive density and throwing it out and updating it every hour, throwing out another 160 odd hours of forecasts with intervals, and you'll start to see they start to sharpen up. Certainly for the first couple of days, they sharpen up, but further on down the line, the intervals are wider. That's 7 days in the future, okay? And we keep rolling this. And so where did this come from? This came from after a couple of years of discussions with our industry partners, and we finally nailed down an operation they had on the northwest shelf where they said, we want to be 80% sure that certain weather conditions will hold before we do this operation. And by the way, we got this data. It takes a couple of years, I've found, to get around to that point where you go, we can do this. We've got a shot at this, although it's going to be a challenge. And this was the result. They had a commercial numeric weather forecast model that they were paying for to do this. We showed them that we categorically blew that out of the water at this point, at this measurement where they were taking this in terms of point-wise predictions, so in terms of root mean squared error, but also pretty well calibrated, certainly in the first few days, with respect to that 80% probability intervals they wanted. So there's a direct probability intervals they want. We gave it to them as software, they packaged it, it is running, they use it. It's supplanted the other one, they love it. Okay, well, it's very lucky my PhD student was a whiz-bang software engineer as well for a while before I got my hands on him. So and we've shown it works across other sites in Western Australia. Other companies have taken it up since then. So it's been a very, very successful tool. And a big part of it was asking about these uncertainty bounds. And there's the spoiler alert, that's where I think our big challenge is going to be in data science. We've accomplished this. I was even told by one of the people in the companies here that this made them millions of dollars. And when I asked how, he said, does that matter? It's a compliment. I said, I'm curious, how did you actually put this together to come up with millions of dollars? Because we've given you better forecasts with uncertainty intervals. Okay, I've said all that. We don't need to see that again. Of course, if we just want to do forecasts themselves, and this has been said beforehand as well, AI models are very, very good at many types of forecasting. They do require a lot of data, but in that case there, we had a lot of data. But quantifying uncertainty is not as yet its strong suit. There's still a lot of effort to go with that. We might talk about standard errors being associated with these sorts of, but a proper probabilistic representation of uncertainty is more difficult. And jumping to the bottom line, if you want to think, maybe a word coherently in there is better, decision making, we really need some good probability reporting, okay? But in any case, what happens if data is sparse and variable? You know, the consequences of decision making are substantial. We do a lot of work in the ocean with these people over there. So at times you're down to 4,000 meters. It can be hard to get data. You know, it's hard to measure fish. It's just that there's it's a hard environment to operate in. Okay, so perhaps decisions are based on inferred causal relationships. Then we really do need some more than black box, quote unquote, kind of model to be able to talk about if a decision wants to be based on how much one variable is affecting another in some sense. And in particular, what happens if multiple stakeholders are affected by the decisions? Okay, a farmer and a miner, or all sorts of things where you can have contrasting benefits or costs. So that leads us to, if you saw in that last, UQ needs to inform robust and risk-assessed decisions. So one way to go about that, this is where I think a big challenge and a big forward thrust, and I don't have answers for it, really, except in a very general sense, is to appeal to decision theoretic type approaches. So what is decision theory? Well, you just pick the best decision. That's fine. But what do we mean by that? Well, the theorists set it up like this. You collect a set of possible actions in A, and you choose one of them. A exists in A. You assign a utility function, U, which is going to map A to R. In other words, it's going to take two different, it's going to take a collection of different actions and put them onto the real number line. Okay, so you've got to be able to think about some sort of numeric quantity you associate with this. And then you pick A with the highest utility. Okay, that makes sense. Now, if the decisions are subject to uncertain outcomes, then that utility function is actually the expectation over that utility function with respect to Y, which is the uncertain outcomes. Okay. So in this sense here, if you have a look at Sam in Casablanca, over in his hotel over the roulette table, your decision at that roulette table will be, do I bet or not bet, perhaps? Okay, if you don't bet, then your utility function will just be it's zero loss. You haven't bet anything. If you do bet, and you bet as a fair bet, $1 to $1, well, then you'll find that on that roulette table, that expected value over mu will give you a negative number, right? The roulette table's not fair. If I put down $1, they put down $1. On average, in the long term, if you like, I'm going to go down, okay? They'll pay you, like a 50-50 bet, but there's more than 18 reds on that table if you're betting on red. Okay, so that's in a simple sense. If you just think about, what am I going to, should I take a bet or not? And I look at most things as taking a bet, whether it be a decision or scientific inference or anything like that, okay? We can easily associate sort of a monetary value to it. The probabilistic process in the background is very easy to understand. It's a good starting block. But of course, I've seen rainfall stuff beforehand today, and me and Sally and others in this room have done a fair bit with it. Yeah, that left-hand panel is just saying, but of course, in the real world, processes are complex. That's hourly precipitation data over about 6 months. You can sit and watch it like a lava lamp for a long time if you like. But of course, that has consequences. Actually, we've seen these two sorts of photos beforehand. One of them was in early January 2020. The other one was in later January 2020, and everything flooded after everything burnt. Events on this side, resulting from these complex processes, have effects like this on the right-hand side. The left-hand side is complex in its mathematics. The right-hand side indicates that it should be complex as well in our utilities and making our decisions. Okay? In other words, how do you even start to think about these things? We can talk about that. If we put it all together, what Sally's stuff was talking about a bit earlier on was this right-hand panel. or this right-hand arc of the curve. What I'm talking about here is when you start to come around to about 9 o'clock and you get the red part, okay? That utility there. That U of A given D is the same U as this fellow here. We are just have a much more complicated system that we're having to integrate over and to average over as its expected value. Okay, but it's the same idea. And we can get to that, but the question really is, what is U? And that is going to be a question to individuals in industry and in the domain sense and all that, because it is very largely a subjective idea, not entirely, but you know, there's monetary costs, there's societal costs, there's climate costs, there's a lot of different costs. I think what it's going to require, you know, he put it very succinctly and nicely back in his book, Howard Rafer, in 1968, maximize your expected payoff, which is the sum of all payoffs multiplied by probabilities. Our probabilities are given by that big complex system going around the first half of the circle. We could have nonlinear PDEs in there and different types of probabilistic wraps around them to describe the noise, etc. Bayesian hierarchical models, that will give us the probabilities of which we take an expected payoff. That is our UA. So that's all very well, that statement. That's great for if you're in Casablanca at the roulette table, although there's other questions that might come about in Casablanca. You might think about harder utilities. But in our modern day, how do we do this? And I think the answer in very general terms is really, really close discussions between the statisticians, the data scientists, the industry partners, the domain specialists. It's a very open question, I think. I think the rest of it, there's a lot of other work under the hood to be done, but I think we're doing that pretty well, even though there's a lot of challenges. But this one, to me, stands out, and I think we want to think about it. Thanks.